It's quite possible that the reader has formed the impression that the author harbors a deep fascination with astronomy. And indeed, despite its undeniable allure, this science possesses one rather disheartening trait. Virtually all of its subjects lie at unimaginable distances from us. Our understanding of the universe is overwhelmingly based on analyzing the light emitted or reflected by celestial bodies. It would, of course, be immensely valuable to have actual, tangible samples for detailed laboratory study. And fortunately, the universe occasionally answers this silent plea, granting us the rare chance to physically touch its mysteries. If you gaze intently at a clear, moonless night sky, and the author strongly urges you to do so, within a few minutes you'll likely spot a meteor streaking across the heavens like a fiery dot trailing a luminous wake. This spectacle ranks among the most astonishing and captivating celestial phenomena, never failing to inspire awe in stargazers. In reality, what you're witnessing is a small interplanetary fragment, be it a stone, an ice particle, or a metallic shard, plunging into Earth's atmosphere and glowing intensely due to extreme heating. Most such fragments appear faint, but some shine with astonishing brilliance. The author once saw a meteor so dazzling that its image burned itself into memory. Clearly, meteors aren't stars, but then, what exactly are they? At times it may seem as though astronomers deliberately use different terms for the same object just to sow confusion. In truth, however, these distinctions serve to clearly differentiate between various cosmic bodies. In this context, the physical object arriving from space is called a meteoroid. The luminous phenomenon produced as it heats up and races across the sky is a meteor. And if it survives the journey to reach Earth's surface, it becomes a meteorite. According to the author, the second best way to irritate an astronomer is to confuse a meteor with a meteorite. The surest way? Asking them their zodiac sign. Scientists who study the cosmos can be surprisingly particular about details. Remarkably, the meteor you see is likely produced by a meteoroid no larger than a grain of sand. How is that possible? The answer lies in gravity. Yes, meteoroids orbit the sun at speeds of tens of kilometers per second. As one approaches Earth, our planet's gravity accelerates it further by an additional 11 kilometers, the escape velocity of Earth. Upon entering the atmosphere, such an object can reach speeds of 70 kilometers or more. This motion carries kinetic energy. Energy must be imparted to set an object in motion and must be removed to stop it. Kinetic energy depends on both mass and velocity, but crucially, on the square of velocity. That means if speed doubles, kinetic energy quadruples. Meteoroids are typically tiny, yet their extreme velocities endow them with substantial kinetic energy. As they collide with our atmosphere and rapidly decelerate, often coming to a near halt, this energy doesn't vanish. Instead, it transforms into light and heat, which is precisely what we observe as a meteor. A common misconception is that meteors heat up due to friction with the air. In fact, the primary cause is pressure. A basic principle of physics states that gas heats up when compressed. A meteoroid traveling at hypersonic speeds violently compresses the air ahead of it, raising its temperature to thousands of degrees Celsius within seconds. This superheated air radiates heat, which in turn heats the meteoroid. Surface materials vaporize and peel away in a process called ablation. These glowing particles trail behind, forming the luminous tail that can remain visible for several minutes, swaying in upper atmospheric winds to leave a ghostly, persistent streak. This all occurs high above us, roughly 90 to 100 kilometers above Earth's surface. From any given location, you can typically see several meteors per hour. While this may seem modest, the total influx around Earth reveals that our planet is bombarded by about 100 tons of cosmic material every day. Still, most meteoroids are minuscule. These random occurrences are called sporadic meteors, often rocky fragments originating from asteroids. When two asteroids collide, they can produce fine debris that continues orbiting the Sun independently. If such debris happens to cross Earth's orbital path, a meteor may result. This process can take millions of years, but eventually, Earth and the meteoroid meet at the same place and time, leading to a collision. Sometimes, however, meteoroids travel in swarms, producing meteor showers with dozens or even hundreds of meteors per hour. Crucially, these showers don't come from asteroids, but from comets. As a comet orbits the Sun, its ice sublimates into gas, ejecting dust and gravel. This material drifts away, but generally remains in the comet's orbital path. Over time, it spreads out along the orbit, forming a diffuse band of cosmic debris around the Sun. When Earth passes through this debris cloud, we witness a meteor shower. From our vantage point, the meteors appear to radiate from a single point in the sky, a perceptual effect similar to driving through a tunnel and seeing wall markings seem to diverge from a point ahead. This point is called the radiant, and showers are named after the constellation where the radiant lies: the Perseids, Leonids, and even the camelopardalids, from Camelopardalis, the giraffe. Because Earth encounters specific cometary debris trails at the same time each year, these showers recur annually. Perseids in August, Leonids in November. November, in fact, hosts numerous meteor showers. Observing a meteor shower requires no special equipment. Just step outside and look up. The best viewing time is after midnight. This is due to Earth's orbital motion. Just as a car's windshield collects more raindrops than its rear window, the side of Earth facing its direction of travel sweeps up more meteoroids. After midnight, you are on that leading side, increasing your chances of sightings. Interestingly, astronauts aboard the International Space Station experience the opposite. They must look downward to see meteors. In 2011, astronaut Ron Garan photographed the Perseids blazing beneath him. Fortunately, the risk of the station colliding with such debris is vanishingly small, thanks to the vast emptiness of space. There is, however, one notable exception to the comet origin rule. The Geminids, visible in December, originate not from a comet, but from the asteroid 3200 Phaethon. This asteroid orbits unusually close to the Sun, heating intensely. The resulting thermal stress causes surface rocks to fracture and vaporize, making it behave like a comet. Most meteoroids entering Earth's atmosphere are small and burn up completely, but some are larger. A bolide, an exploding meteor, is an exceptionally bright event caused by a meteoroid roughly the size of a grapefruit. Such fireballs often occur over populated areas, and many people have witnessed them firsthand. A few meteoroids survive atmospheric entry and strike the ground as meteorites. The immense pressure during descent often causes them to fragment or explode, scattering dozens or hundreds of pieces. These fragments quickly slow after their fiery descent and simply fall to Earth. The upper atmosphere is cold, and the interiors of these objects remain frigid from their long sojourn in space. So contrary to popular belief, meteorites rarely start fires upon impact. They may even feel cold to the touch. Meteorites are classified into three main types, based on composition: stony, mostly rock; iron, mostly metal; and stony-iron, a mix of both. Most are stony and fall into two subcategories: chondrites and achondrites. Chondrites contain tiny mineral grains and are considered primordial, likely formed by condensation from the original solar nebula. Their age is determined by analyzing ratios of elements produced by radioactive decay. The oldest known meteorite solidified 4.568 billion years ago, before Earth itself formed. Achondrites lack these grains and are thought to be fragments of a larger asteroid that once melted, allowing minerals to mix. A catastrophic collision shattered that parent body, producing today's achondritic meteorites. Iron meteorites likely originate from the cores of massive asteroids whose gravity caused metals to sink inward. A violent impact later broke apart such a body, scattering its core material through the asteroid belt, some eventually crossing Earth's orbit. Stony-iron meteorites are the rarest. Some, known as pallasites, feature stunning green or orange olivine crystals embedded in a metallic matrix, among the most beautiful space rocks known. Meteorite collecting is a fascinating, though sometimes expensive, hobby. Anyone interested in acquiring specimens should purchase only from licensed dealers. Occasionally, however, an incoming meteoroid is large enough to cause catastrophe. On February 15, 2013, residents of Chelyabinsk, Russia, witnessed a sudden, dramatic event. At 9:20 a.m. local time, a roughly 19-meter-wide rock entered the atmosphere at a shallow angle, glowing nearly as brightly as the sun. Atmospheric pressure caused it to fragment explosively, releasing energy equivalent to 500,000 tons of TNT, comparable to a small nuclear bomb. Fortunately, no one died, but over 1,000 people were injured by flying glass shattered by the shockwave. Many were looking out windows at the smoke trail when the blast hit. There had been no warning. The asteroid was too small to detect with existing telescopes. But that may soon change. New observatories are expected to come online in the near future, capable of spotting smaller, near-Earth objects and providing early alerts. Astronomers are most concerned about asteroids 100 meters or larger, which could devastate entire cities, and are still difficult to detect in time. What if we discover such an object on a collision course with Earth? Currently, humanity lacks the capability to prevent impact. Proposed solutions include detonating a nuclear device nearby or crashing a spacecraft into it to alter its trajectory. Ideas that sound promising in theory, but remain untested. Practical implementation is likely years away. The good news? Impacts of this scale are rare, occurring roughly once every century or 3. But without action, one is inevitable. Science fiction writer Larry Niven once quipped that the dinosaurs went extinct because they lacked a space program. Humanity, he implies, must be wiser. Today we know meteors are small fragments of cosmic debris shed by asteroids and comets. When Earth crosses a comet's debris trail, we witness a meteor shower. Most meteors burn up about 100 kilometers above the surface, but some reach the ground as meteorites, mostly stony, some iron, and a few stony-iron. While extremely large impacts can be catastrophic, humanity is determined to take every possible measure to avoid sharing the dinosaurs' fate.